Hoover Dam contains so much concrete that it could build a highway across the United States. But before any of it was poured, the Colorado River had to be defeated. Deep inside Black Canyon, engineers drilled into solid rock, blasting massive diversion tunnels through the canyon walls and forcing the river to change its path. Cableways then lifted concrete across the canyon as the dam rose from bedrock, while penstocks and powerhouses were carved deep into the rock. When the river finally returned, it flowed through turbines and generators, transforming raw force into controlled power. This is the hidden engineering that made Hoover Dam possible. In this video, we break down the hidden engineering behind Hoover Dam, from river diversion to a fully functioning hydroelectric machine. Choosing the right location for the dam was one of the earliest and most critical decisions. Engineers first considered Boulder Canyon, but geological studies showed its rock wasn't strong enough to hold such an enormous structure. So the site was moved 6 miles downstream to Black Canyon, a far better choice. Its walls were made of hard dolomite rock, perfect for supporting millions of tons of water, and the river flow there was nearly twice as strong, allowing the future dam to generate much more power. Black Canyon also offered a narrower gap, which meant a shorter, more efficient dam could be built. In the early construction phase, engineers needed a way for workers to cross the deep Black Canyon quickly and safely. With no roads or permanent access routes, they built temporary suspension bridges made from timber planks and wire cables. Though simple and swaying in the wind, they were essential early lifelines that made large-scale construction of Hoover Dam possible. Before a single cubic yard of concrete could be poured, engineers first had to dry out the riverbed where the dam would stand. This required an enormous and risky undertaking, diverting the entire Colorado River away from the construction zone. To do this, workers drilled 4 massive diversion tunnels, each 56 feet in diameter, through the canyon walls, 2 on the Nevada side and 2 on the Arizona side, for a combined total of 16,000 feet of tunnel. Francis Trenholm Crowe, the chief engineer responsible for directing the entire Hoover Dam construction, knew that the first major task was to divert the Colorado River through massive tunnels carved into the canyon walls. Before the massive diversion tunnels could take shape, engineers first had to create smaller access passages known as adits, critical openings that allowed crews to reach deep into the canyon wall long before the main excavation even began. These adits were positioned at the midpoint of each planned diversion tunnel, giving workers a direct route to the downstream face of the future dam foundation. These adits were roughly 10 feet wide and 8 feet tall, stretching nearly 700 feet into solid rock, and took about 3 months of non-stop work to complete. The first drilling began from boats on the river, where crews used heavy pneumatic drills with hardened steel bits to cut into the rock. The drill, also known as the drifter drill, was mounted on adjustable platforms and used compressed air to drive a steel bit rapidly into the canyon walls. The bit itself was a hardened steel rod with a chisel-shaped tip, designed to withstand intense impact as it cut through solid rock. Together, they created the deep, precise blast holes needed for dynamite, allowing engineers to control exactly how each section of the canyon wall would fracture. Once all the holes were packed, crews cleared the area and the dynamite was fired, shattering the canyon walls and pushing the excavation forward blast by blast. When the adits finally met the diversion tunnel alignment, workers opened 12 by 12 foot tunnel headings from both the midpoint and the tunnel entrances, allowing multiple crews to drill, blast, and remove rock at the same time. By attacking the excavation from several directions simultaneously, progress increased dramatically. cutting months off the construction schedule as the tunnel sections steadily advance toward one another deep inside the canyon. The excavation starts with a 12 by 12 foot pilot heading driven straight into the canyon rock. To keep the drilling steady and accurate, the rock drills are mounted onto metal braces and pipes anchored against the tunnel walls. Instead of a single drill, several are set up at once, with an operator assigned to each one. To drill these massive sections efficiently, Crow's solution introduced a revolutionary new piece of equipment, the drilling jumbo. This machine was essentially a 10-ton flatbed truck with a platform built on top, carrying 31 pneumatic drills that could all operate simultaneously. This allowed workers to drill dozens of holes at once, each 5 to 8 feet deep, which were then filled with dynamite and blasted away. The impact on productivity was dramatic. Suddenly, crews could excavate as much as 260 feet of tunnel every 24 hours, achieving an astonishing pace of 1.2 miles in a single month. After excavation was completed, the diversion tunnels required a structural lining capable of withstanding extreme water velocities and long-term erosion. The raw tunnel surfaces were first scaled and cleaned to remove loose rock and debris, ensuring proper bonding between the concrete lining and the surrounding bedrock. The lining of the diversion tunnels relied on specialized equipment designed for precision work in confined underground spaces. Curved steel lining forms defined the final tunnel shape and were installed in short modular sections. These forms were supported by rail-mounted carriers and adjusted with mechanical jacks to maintain accurate alignment during concrete placement. Concrete was delivered using buckets, chutes, or pipelines, depending on location, and consolidated with internal vibrators to eliminate voids and ensure full contact with the surrounding rock. Concrete placement followed a sequenced structural pour. The process started at the tunnel invert, where concrete was placed and compacted to form a stable base. Placement then progressed symmetrically up both sidewalls to prevent unbalanced loading on the formwork. For sidewall lining, crews used a sidewall jumbo, a mobile steel platform operating along the tunnel length. Curved steel forms were mounted and braced to maintain the correct tunnel profile from the invert to the spring line. Concrete was delivered from above through metal concrete chutes attached to the forms, directing the flow in a controlled manner to prevent segregation and reduce pressure on the forms. After the concrete gained sufficient strength, the forms were removed and the jumbo advanced forward to repeat the process along the tunnel. Finally, the uppermost portion of the tunnel lining was the most technically demanding stage. By the time crown concreting began, the invert and sidewalls had already cured sufficiently, forming a stable base to support additional loads. To place the crown, tightly sealed steel formwork enclosed the upper arc of the tunnel. The forms were engineered to resist uplift and prevent leakage, since fresh concrete can sag or segregate when placed overhead. Access ports, known as crown windows or grout holes, were built into the formwork to enable controlled placement and release trapped air. After the concrete lining was completed, the 56-foot diameter diversion tunnel was prepared for post-lining grouting. Although the lining formed a smooth, continuous surface, small voids could still exist between the concrete and the surrounding rock. Left untreated, these gaps could allow seepage, reduce load transfer, and concentrate stresses behind the lining. To address this, engineers drilled a systematic pattern of grout holes through the concrete lining and into the surrounding rock. Through these openings, a cement-based grout was injected under carefully controlled pressure. The grout flowed into remaining cavities and fractures, filling voids and bonding the lining tightly to the canyon walls. Once complete, the diversion tunnel functioned as a unified structural system, capable of safely carrying high-velocity river flow without leakage or loss of stability. With the diversion tunnels fully prepared, a series of small controlled blasts were used to cut a pilot channel in the riverbed, directing the Colorado River toward the 56-foot diameter diversion tunnels. These tunnels had been deliberately overbuilt to handle extreme flood conditions, allowing engineers to operate 1 or 2 tunnels depending on river flow. Once the river was successfully guided into the tunnels, site dewatering could begin. As water levels dropped behind the diversion, construction crews moved rapidly to build the upstream and downstream cofferdams, sealing off the dam site and transforming the once raging riverbed into a dry construction zone ready for excavation and foundation work. A coordinated fleet of shovels, trucks, and heavy equipment immediately began removing the accumulated sediments to reach sound foundation material. This excavation extended approximately 135 feet below the original river channel and required the handling of more than 2 million cubic yards of rock, sand, and silt. The effort pushed both manpower and machinery to their limits, especially when hauling material out from the deepest sections of the canyon. With the riverbed excavated to competent rock, attention shifted to preparing the abutments, the steep canyon walls that would anchor either side of the dam. Just as with the foundation, the abutment rock had to be exposed, cleaned, and brought to a structurally reliable surface. Cable lines swung workers into place against the near-vertical canyon walls, where they attacked loose and weathered rock using scaling bars, chisels, and pneumatic jackhammers. The jackhammers hammered hardened steel bits into the rock, breaking through weak layers and revealing solid bedrock. Building a dam of this size wasn't just about producing concrete, it was about getting that concrete exactly where it needed to go. To solve this problem, engineers built an ingenious aerial cableway system right over Black Canyon. This system consisted of 10 parallel high lines stretching across the canyon like giant clotheslines. On the Nevada side, at the canyon rim, they constructed a head tower, a tall, movable structure that anchored one end of the cables. On the Arizona side, another stationary tower served as the fixed anchor point. Besides the temporary cableways, one permanent cableway system was installed across Black Canyon to handle the main structural lifting operations. 2 steel towers were anchored into the canyon rims. Between them, massive steel track cables were stretched across the gorge, forming a calculated catenary curve designed to carry extreme tensile loads. A powered trolley traveled along these cables. Suspended below it, a vertical hoist line and a 25-ton concrete bucket. The lifting machinery was controlled from the hoist house, a reinforced structure positioned on the canyon rim. With the cableway system in place, the concrete operation had to run as a continuous synchronized process. Cement was delivered by purpose-built rail lines serving the project. Freight cars transported bulk cement and aggregates to the batching plant located on the rim above Black Canyon. The materials were transferred into silos and aggregate bins, then proportioned by weight to ensure consistent structural performance. From there, they entered large rotating mixers designed for high-volume mass concrete production. But that was not the only plant. A secondary mixing plant was installed at the bottom of the canyon near the foundation level. After mixing, the concrete discharged into steel buckets positioned below the plant, each capable of holding up to 20 cubic yards. The permanent cableway then took over. A trolley engaged the bucket. The hoist lifted it clear of the platform, transported it across the canyon span, and lowered it several hundred feet to the excavation floor. Inside the hoist house, operators precisely controlled trolley travel, descent rate, and final alignment using powered winches and braking systems. At the foundation level, steel forms had already been secured against cleaned bedrock. The bucket gate opened, releasing concrete into the forms. Crews distributed and vibrated the material to eliminate voids and achieve full consolidation against the rock interface. This marked the first structural block of Hoover Dam constructed not as a single monolithic pour, but as a sequence of interlocking blocks placed systematically as the dam rose from the canyon floor. Every block was designed with interlocking geometry. The sides were keyed and stepped, forming shear keys that mechanically locked adjacent blocks together. Rather than relying only on bond strength, the dam used geometric interlock to transfer loads across joints. Concrete was placed in lifts, one layer at a time. After partial curing, each surface was cleaned and roughened before the next lift was added. Vertical contraction joints were built between blocks to control thermal cracking as the mass concrete cooled. Inside selected blocks, internal passageways called galleries were formed to allow inspection, drainage, and monitoring within the structure. As concrete placement progressed, engineers faced a major thermal challenge: the heat of hydration. When cement reacts with water during curing, it releases heat. In ordinary structures, this heat dissipates naturally, but the massive volume of concrete at Hoover Dam could trap heat and raise internal temperatures dramatically. To control this, a large cooling system was embedded directly inside the concrete. Miles of thin steel pipes ran through each block, circulating cold water to remove heat from the curing concrete and lower its internal temperature. Once the concrete stabilized, the pipes were filled with grout and permanently sealed inside the dam. With the main structure of Hoover Dam in place, engineers constructed another critical component: the intake towers. These tall concrete structures stand upstream of the dam within the reservoir. Their purpose is to control how water enters the hydroelectric system. Structurally, the towers were built using the same method as the dam itself. Concrete was poured in stages within heavy formwork, while dense reinforcing steel bars were embedded throughout the structure to provide strength and resist hydraulic forces from the surrounding reservoir. At the entrance of each intake, heavy steel trash racks are installed. These vertical steel grates act as protective screens, preventing floating debris such as driftwood, vegetation, or large objects from entering the water conduits. Each intake tower contains two main inlet openings, one located near the bottom and another at the mid-level of the tower. Each inlet is about 9 feet tall and fitted with protective trash racks. Under normal operation, only one inlet is opened at a time, allowing operators to control the depth from which water is drawn from the reservoir. Inside each intake tower, the flow of water is regulated by large intake control gates. Each gate is a massive steel plate that slides vertically within guide slots built into the concrete tower. The gates are operated from machinery rooms inside, where electric motors drive hoisting systems connected to the gate stems. When raised, water from Lake Mead flows through the intake and into the penstocks leading to the turbines. When lowered, the opening is sealed, completely stopping the flow. A total of 4 intake towers were built to serve the system. From each tower, water flows into massive 30-foot diameter penstocks, which carry it downward through the canyon walls. These penstocks then intersect with the former diversion tunnels, which were modified and integrated into the permanent system. At these junctions, tunnel plugs were constructed, massive concrete barriers placed inside sections of the diversion tunnels. These plugs sealed off unused portions of the tunnels and redirected the water into the penstocks and power system. With the diversion tunnels partially closed and controlled by tunnel plugs, the flow was fully managed and directed toward the turbines in the powerhouse. The 2 outer tunnels were also modified and repurposed as spillways, designed to release excess water during high reservoir conditions. Control gates installed at the intake structures regulate when water enters the spillway tunnels. Once opened, water flows through the tunnels at extremely high velocity, bypassing the dam structure. To handle this energy, the tunnels were reinforced with smooth concrete lining to reduce friction and resist erosion. At the downstream end, outlet structures dissipate the energy before the water re-enters the river channel, preventing damage to the canyon walls and foundation. In this configuration, the outer tunnels act as a critical safety system, protecting Hoover Dam from overtopping during floods by providing a controlled escape path for excess water. Over time, the outer tunnels were gradually closed using bulkhead gates. As these gates were lowered, flow through the spillway tunnels was restricted, allowing the reservoir to begin rising behind the dam. With the diversion system no longer needed for continuous flow, water levels increased steadily, forming Lake Mead. As the water level rose, the intake towers became fully operational, directing flow through the penstocks to the turbines, marking the transition from construction to a functioning hydroelectric system. Back to the intake towers, water enters the system through the controlled inlets and flows into massive steel penstocks, each about 30 feet in diameter, carrying it downward under high pressure toward the powerhouse of Hoover Dam. As the water descends, its potential energy is converted into high-velocity flow, building the pressure needed to drive the turbines. Constructed from thick steel plates, the penstocks were riveted, welded, and firmly anchored into the surrounding concrete. Supports and expansion joints were added to handle thermal movement and reduce stress along the pipes. Near the powerhouse, the main penstocks branch into smaller pipes, distributing water evenly to each turbine. Flow control valves regulate the supply before the water enters the generating units. These flow control valves are massive butterfly valves installed within the penstock system. Inside each valve is a large circular steel disc mounted on a rotating shaft. When the disc rotates parallel to the water flow, the passage opens and water moves freely. When rotated perpendicular to the flow, the disc blocks the passage and restricts or completely stops the water. Before water enters the generating system, let's first take a look at the powerhouse, where the key equipment is located. At Hoover Dam, the powerhouse is where water energy is converted into electricity. Situated at the base of the dam on both the Nevada and Arizona sides, it forms two long symmetrical wings. Inside, large vertical axis turbines and generators are arranged in a row, with each turbine directly connected to a generator above. The powerhouse also houses control systems, transformers, and other electrical equipment used to regulate and transmit the generated power. Now, returning to the water flow. From the penstocks, high-pressure water enters the turbine through a spiral case inside the powerhouse of Hoover Dam. The spiral case wraps around the runner and narrows, distributing water evenly while increasing velocity. The flow then passes through adjustable wicket gates, controlling the rate and direction before striking the turbine blades. As the water hits the runner, it forces it to rotate. Each unit producing around 178,000 horsepower, contributing to nearly 3 million horsepower in total, converting hydraulic energy into mechanical motion. This rotation drives the generator shaft, producing electricity through electromagnetic induction. At the top, the generator converts mechanical rotation into electricity. A massive rotor spins inside the stator, driven directly by the turbine shaft. The rotor carries heavy metal windings, while stationary windings in the stator surround it. As the rotor spins, it generates an electric current through electromagnetic induction. At the top of each generator, the exciter supplies the current needed to create a magnetic field in the rotor. This magnetic field is essential. As the turbine spins the shaft, the energized rotor rotates inside the stator, inducing electrical current through electromagnetic induction. The generated electrical current is then routed out of the powerhouse of Hoover Dam to large transformers located outside. Here, the voltage is stepped up for efficient long-distance transmission. From the transformers, the electricity is carried by heavy transmission lines that climb up the canyon walls. These lines are supported by distinctive tilting pylons, engineered to align with the steep geometry of the canyon. The entire layout is symmetrical. The Nevada side mirrors the Arizona side with identical transmission systems on both ends. At the center, between the two powerhouses, sits the administrative building, which manages operations and control of the dam. Beyond the powerhouse, another key structure comes into play: the valve houses of Hoover Dam. These rectangular structures sit partway down the canyon walls and connect directly to the Penstocks. Inside, they house massive control valves used to regulate or bypass water flow. The most prominent are needle valves, large, precisely machined units designed to handle extremely high-pressure water. When opened, they release powerful jets into the river below, bypassing the turbines. This allows operators to control discharge during maintenance, startup, or emergency conditions. Structurally, the valve houses are built from reinforced concrete to withstand strong hydraulic forces and vibration. From the outside, they appear as standalone towers, but internally they act as key control points within the water system. In operation, the valve houses provide flexibility and safety, allowing water flow to be managed independently of electricity generation when required. Further inside the system, the lower Penstocks terminate through tunnel plug outlets built within sections of the former diversion tunnels of Hoover Dam. Engineers constructed massive reinforced concrete tunnel plugs that sealed portions of the original tunnels and redirected water into the permanent intake and outlet network. Built into these plug structures were 12 additional needle valves housed inside reinforced concrete valve rooms. These valves provided another controlled outlet for releasing water under pressure. Water approaching from the diversion tunnel sections could be isolated by bulkhead gates, then routed through the valve chambers. When the needle valves opened, high pressure flow discharged safely downstream. This arrangement transformed the temporary diversion tunnels into permanent hydraulic control structures, giving Hoover Dam greater flexibility for flow regulation, maintenance, and emergency release operations. Finally, the most visible overflow protection system is the well-known spillways of Hoover Dam. Located on both the Nevada and Arizona sides, these large open-channel spillways sit high above the dam crest near the reservoir. When Lake Mead rises beyond normal operating levels, water can enter the spillway inlets and be diverted away from the dam. From the intake crest, the flow drops into steep spillway tunnels excavated through the canyon walls. These tunnels connect to the repurposed outer diversion tunnels, carrying enormous volumes of water at high velocity. At the downstream end, specially designed outlet structures dissipate the energy before the water re-enters the Colorado River. This prevents erosion and protects the canyon walls and dam foundation. The spillways serve as the final safeguard of the entire system, providing a controlled route for excess floodwater when reservoir levels rise too high. Beyond its engineering role, Hoover Dam also became a major public destination. Multi-level parking garages were built near the canyon rim to handle visitor traffic, while a nearby visitor center explains the dam's history, construction, and operation through exhibits and displays. Observation areas and guided routes allow visitors to view the dam crest, intake towers, Powerhouse, and Lake Mead from above. What began as a massive engineering project also became one of the most visited landmarks in the American Southwest. From a remote canyon with no roads or access, Hoover Dam became one of the greatest engineering achievements of its time. Nearly a century later, Hoover Dam still controls water, generates electricity, and stands as a lasting symbol of large-scale engineering.